Welcome to another exciting calc video. In this one, we're going to finish up section 4.2. In the last video, we did examples 1, 2, 3, and now we're going to finish this section off. So let's see here. There we go. Where did we leave off? Yeah, there was example 3. Here's example 4 coming up after we talk about upper sums and lower sums, over and under estimates. So the procedure we saw in example 3 can be generalized as follows. Consider a flat plane region bounded above by the graph of a non-negative continuous function. So with non-negative, we're going to be in quadrants 1 and 2. Our function will be continuous, no holes in it. So the region bounded below by the x-axis and on the left and right by the vertical lines x equals a and x equals b. So here our top is the function, the bottom is the x-axis, our left and right boundaries are some lines x equals a and x equals b. So to figure out an approximation of the area of that region, first we would subdivide the interval from a to b into n subintervals, 10 or 100 or 1,000,000 subintervals, whatever we want n to be. And that is our delta x, the base of our rectangles, b minus a, all divided by n. So the endpoints of these intervals, now in the last examples, all of our areas started right at the y-axis. Here, we've actually got a little gap in there. So we're not starting right at 0, we're starting at some number a. So what they're doing here for our subintervals, we've got the left endpoint a. A lot of times that's going to be a 0 plus 0 delta x, and that will be less than a plus 1 delta x, which is less than a plus 2 delta x, dot, 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 all the way to the last rectangle, the nth rectangle. Now, because the function's continuous, the extreme value theorem will guarantee the existence of a min and a max on each of those subintervals. To distinguish between them, we use upper and lower case. So f of lowercase m sub I is the minimum value. F of capital M sub I is the max value. Next, we define an inscribed rectangle as lying inside that subregion. Circumscribes extend beyond the function curve. The height of that ith inscribed rectangle, f of lowercase m sub I, and the height of the ith circumscribed rectangle, f of capital M sub I. For each I, the area of the inscribed is less than or equal to that of the circumscribed. The area of the inscribed rectangle is our f of lowercase m sub I times delta x, base times height. And that is always going to be less than or equal to f of capital M sub I times delta x, base times height. The sum of the areas of the inscribed rectangles is called the lower sum. The sum of the circumscribed is called an upper sum, our lower or our under and over estimates. So the lower sum, we use lowercase s of n. That is our summation of the mins, f of lowercase m sub I delta x. The upper sum, the overestimate, is capital S of n. It's the sum of all the rectangles using the max of that interval, f of capital M sub I delta x. So from the figures below, we can see the lower sum is less than or equal to that of the upper sum. Moreover, the actual area, the true area, lies somewhere in between. So here is our overestimate. The true value will always be less than or equal to that. And our underestimate here is always less than or equal to the true value, our circumscribed and inscribed rectangles. So here in example 4, we're going to find the upper and lower sums for x squared. We're going to find the area of the region under x squared, but above the x-axis from 0 to 2. Here on this one, we see we are underneath the the curve. All our rectangles are inscribed. We will do it again here when they extend beyond for the circumscribed rectangles. And I'm just going to make a new slide right now and drop that on there because I don't want it taking up any space over here. Find the upper and lower sums for the region bounded by the graph of x squared. The x-axis between x is 0 and x is 2. So what we're going to have to do first is cut our interval from 0 to 2 up into, that's supposed to be an n rectangles or intervals. So the region from 0 to 2 we're going to chop up into n intervals. N will represent any number of rectangles we want, from 10 to 10,000 to 1,000,000 to infinity. And now we're going to find our delta x right here. The base of each rectangle is b minus a over n, our bigger x value minus our smaller, divided by the number of rectangles we want. So our delta x, the base of any rectangle, is b minus a over n, or for this problem, 2 minus 0 over n, which is just 2 over n. Now our function x squared is increasing, so our left endpoints will be an underestimate, our right endpoints will be an overestimate. The bigger we let n become, the estimate becomes closer to the true value. Now, we are going to do left and right hand sums, so let's get our endpoint formulas out of the way. Let me do it like this. Endpoint formulas. So we'll do the left endpoint formula on the left, the right endpoint on the right, naturally. Left and right. Now usually the right endpoint is going to be a little bit easier than the left. In this case, let's stick to the book's notation, capital M sub I. That would be equal to, and again, because, it has here our left endpoint a plus that. Remember on ours, right now, our left endpoint is 0, because we are starting right here at the origin. So we could put in there 0 plus, take your delta x, your 2 over n, and multiply it by I. So usually, if you're starting at 0, the right endpoint, 99 times out of 100, is your delta x times I. And let's see if that would work. Let's say here, they're chopping this up into 5 rectangles, 1, 2, 3, 4, 5. So let's assume our n is 5, so each of those rectangles' bases would be 2/5. So here's 2/5, 4/5, 6/5, 8/5, 10/5 does reduce to 2. And if I want to get to the right-hand end of that first rectangle, that would be at 2/5. I would put a 1 in for this I. So that would be 2/5 times 1, or 2/5. That will take me to my right endpoint. Now, I do the right endpoint first because that might make it easier to find the left, lowercase m sub I. What we want to do is plug in a number for our rectangle, for I. When we plug in a 1, we want to get back to 0. So what I'm going to do is take my right endpoint and replace the I with an I minus 1 times 2 over n. And let's go back. If I try to put in, to get to the left endpoint, here we want to get back to the origin. So if I plug in a 1 for that I for the first rectangle, 1 minus 1 is 0, times it by the delta x, we get back to 0. So here's our left and our right endpoints. Now we're going to do the trickier one first. We're going to do this left endpoint first, our lower sums. And I don't want to erase this, so I'm just going to start yet another slide. And I'm going to call this lower sums, or in parenthesis, left endpoints. So we're going to do a summation from I equals the first rectangle to the nth, the last, and that is going to be f of lowercase m sub I times delta x. Remember, in the big picture, we're finding areas of rectangles. This is the height of the rectangle dictated by the function. This is the base. Base times height is the area of our rectangle. So let's put this now, function notation, with our actual endpoint formula. So this is going to be f of 2 quantity I minus 1 over n times 2 over n. So again, this 2 over quantity I minus 1, I sort of just put this, let me do a black parenthesis, I just put this up here with the 2. Okay. Again, remember the f of stuff, that's the height. The 2 over n is the base, of our rectangle. Get out of the, there we go. Okay. So again, this is base times height. So we're going to jump now from the function notation to actually put this into the function. Remember, our function here is x squared. Move it over here. Where is it? X squared is our function. So this f of is going to become something squared, and that's going to get multiplied by our 2 over n. And what we put in there is our 2 I minus 1 all over n. Okay, so we've gone from the function notation into the function, and now we want to do some algebra and simplify as much as we can. Remember, if it's got n's, we can pull it out in front of the summation. After the summation, we just want i's. So it's algebra. Well, actually, first off, no, let's save that for the next step. So from I equals the first to the nth rectangle, let's square this quantity. So the square is going to hit this 2. That's going to square to a 4. We're going to have our I minus 1 in parenthesis. That will be squared. Our denominator n also gets squared. And then we still have this 2 over n. Now, before we actually use our formulas, we want to get as much stuff out in front of the summation as we can. So I'm going to put my summation right about here. And let's see what we can pull out. This denominator is an n squared, and we're going to multiply it by this denominator n. So that's an n cubed is now outside the summation. And then we've got this 4 times this 2. That is an 8. Oops, get out of the way. And then that just leaves this I minus 1 quantity squared. Let's FOIL that out. I squared minus 2i plus 1. Okay. Now, I'm going to introduce a blue set of brackets because that 8 over n cubed is applied to this whole thing. So what I like to do is save this 8 over n cubed to the end. 8 over n cubed. Now let's distribute that summation symbol. So we are going to have a summation, and I'm going to, for a minute here, I'm going to stop my upper and lower bounds. We're going to have a summation of I squared. And that's okay because we got a formula for that. And then we're going to have minus, in our next summation, let's factor the 2 out here in front and just leaving that as the summation of I, because we got a formula for that, plus the summation of 1. Now this one on the end, I am going to put the limits, our lower limit would be from 1 to n. All right. So we are at a point, we can actually, oops, what the heck was that? There we go. We can actually apply and use our summation formulas. So 8 over n cubed, that comes along for the ride. And I'm going to block it off here in green ink. This summation of I squared, we can replace that with n times n plus 1 times 2n plus 1 all over 6. minus, we've got a 2. I'm going to write that as 2 over 1. And then we've got this summation of I. Well, we got a formula for that. That is n, times n plus 1 all over 2. And I wrote just a little too big, but I can do this. Shrink it up a little bit. Now the last one, we have a summation of 1. Remember, if we're summing a constant, we just multiply the upper bound times that constant, so that becomes 1 times n, or just n. I'm going to put it as n over 1. Okay, close off that bracket. Now, if you don't see something like this when you're doing your homework, don't worry, it's not going to give you the wrong answer. But here we can do something to make our lives a little easier. Notice we have 3 terms in the brackets. Here's the first one, and then the second one, and then the third one. Each of the numerators has an n. So this n, and we have this one here, and we have this one here, and we have an n cubed outside in the denominator. So what we can do is cancel these multiplied n's here. Now remember, this is going to turn into a 1. It's not just going to disappear. And we're going to knock this down to n squared. So what we have now is 8 over n squared, and that's going to make our algebra in the brackets a little easier. Our first term here, I'll stick with the blue ink. Denominator is 6, and we're going to FOIL out that numerator. That's going to be a 2n squared plus n to plus 3n plus 1. And then on the next term, I'll go back to red ink, minus. On the diagonals here, we can cancel the 2's. Now mind, we have a negative here, so we would distribute that negative. So minus n minus 1. Minus n minus 1, and that is all over 1. What's next? Plus 1 over 1. Plus 1 over 1. All right. Oops, get back there. Okay, I guess we can just distribute the 8 across the entire numerator and the n squared across the entire denominator. So if we distribute the 8, we're going to get 16n squared plus 24n plus 8 all over 6n squared minus 8n minus 8 over n squared plus 8 over n squared. Now, I believe in the book they break the first 2 up into individual pieces. You know, you'd have a 16n squared over 6n squared, 24n over 6n squared, 8 over 6n squared. But we really don't have to, because remember now, n represents the number of rectangles. More rectangles are better. So we are going to look at this as a limit as n approaches infinity. Infinity is the best number of rectangles. Now remember about the power struggle between the numerator and denominator when n gets infinitely large. In the first term here, what's more powerful, numerator or denominator? It's a tie. So we make a leading coefficient fraction. So that, when we let n go to infinity, is going to equal 16 over 6, or 8/3, minus, we've got another term, I'll circle it here in blue. What's more powerful, numerator or denominator? Denominator is more powerful. That chunk is heading for 0. Plus, we've got 8 over n squared. What's more powerful? Obviously the denominator. That's also heading for 0. So this is our, again, kind of an underestimate, but it's not really an estimate when we let n go to infinity. The area under that curve is equal to 8/3 square units exactly. Whew, that was pretty tiring. But again, we're going to do this both ways, and what we just did here was the hard way. When we do the right endpoint formula, the computations will be much easier. And spoiler, we're going to get to the exact same answer 8/3, because remember, it's no longer an estimate. We're now actually finding the true value. We're letting n get so large, the error shrinks to 0, and we have the true value. So let's do all that again, doing right endpoints. That will be our circumscribed rectangles. Technically, this is kind of going to be an overestimate. So remember, for these upper sums, we use capital. So this will be capital S of n is going to be our summation from I equals the first rectangle to the last, the nth, f of capital M sub I times delta x. F of the function is our height, delta x is the base. Now we're going to go back and use this endpoint formula, just 2I over n. Yeah, we can, put that I up there with the 2I over n. So we're going to have our summation from I equals the first to the nth rectangle, f of 2I over n times delta x is 2 over n. Now we're going to make the jump from function notation to actually jumping into the function. And remember, our function was some quantity squared. What are we squaring? 2I over n. And of course, out here, we have our 2 over n. Now you're going to see why this is so much easier than the last one, because of the algebra involved. So first, let's square that quantity. 2I times 2I is 4I squared, divided by n squared. And then we've got times 2 over n. Okay, it's already looking much, much easier. Let's see what we can pull out front of our summation symbol. I equals our first rectangle to our last. Well, let's see here. We've got an n squared times an n in the denominator. That's going to get dragged out front, and it should stay in the denominator, n cubed. Oop. There we go. Numerator, just like the other method, 8 times 2, 4 times 2 is 8. Getting a little ahead of myself. So what does that now leave us after the summation? Just an I squared. Ooh, much, much easier to deal with. And I chopped off the top of my 8. Let me fix that. There we go. So 8 over n cubed. Now here is a summation of I squared, and we have a formula for that. That is n times the next number up, n plus 1, times 2n plus 1, all over 6. All right. Look for that n cancellation on the diagonal. If you don't catch it and cancel, you'll still get the right answer at the end. But this n is going to cancel with one of these, so now that's down to squared. So I'm just going to drag this 6 out here with this n. So that's going to be 8 over 6n squared. And now in here, we're going to FOIL out these two red binomials. So as we start foiling, we're going to get a 2n squared plus a 3n plus a 1. And that's all. Well, that 6 we dragged out. So that's over 1 now. Okay, let's distribute the 8 over 6n squared and apply the n goes to infinity limit. So distribute the 8, we're going to get a 16n squared plus a 24n plus 8 all over 6n squared. All right, apply the limit. Let n go to infinity. Infinite triangles are the best, so the limit as n heads to infinity. So we look at the leading terms, the power struggle. What's more powerful? It's a tie. Those are going to cancel. So we're left with, let's reduce it down to 8/3. That sounds very familiar because that was the answer we found with the left-hand sums. The right-hand sums gave us the exact same answer. So let me let that sink in. There's a hard way and an easy way to do these. One endpoint formula is trickier. It's got more algebra. The other one is usually much easier, but they came to the same answer. Upper sums 8/3, lower sums 8/3. It doesn't matter which way we go, as long as we let n go to infinity, we're going to get the correct answer either way. All right. And when we learn the shortcut, you will be able to do those computations in less than 30 seconds. Okay, and here I think where the book hammers it home. Example 4 illustrates some important things about upper and lower sums. First, notice that for any value of n, the lower sum is equal to or less than the upper sum. Second, the difference between the two sums lessens as n increases. In fact, when you take the limit as n goes to infinity, both approach 8/3. Here's where they broke it into separate fractions. So lower sums and upper sums. Notice the only difference is right here. Everything after that's the same. When n gets infinitely large, these turn into zeros, these turn into zeros, so it doesn't matter if we're subtracting or adding, we're subtracting or adding nothing. So in this case, it come down to our first term. 8/3 was the area. Now, we're going to look at a theorem coming up next. It shows that the equivalence of these limits as n goes to infinity of the upper and lower sums is not a mere coincidence. It's true for all functions that are continuous and non-negative on our closed interval. The proof of this theorem is best left to a course in advanced calculus. They don't even want to put that proof in the appendix to our book because it is not nearly advanced enough. All right, and here it is, Theorem 4.3. We let our function f be continuous and non-negative on some closed interval. The limits, as n gets infinitely large, of both the lower and upper sums are equal to each other. So here, this all starts with the limit as n goes to infinity of lowercase s of n, and it's going to end at its being equal to the limit as n goes to infinity of the capital S of n, the upper sums. So the lower sums are equal to this limit, the sum of all the rectangles of the mins of the rectangles times delta x, and that's going to give you the exact same answer as if you do the summation of the maxes on each of those rectangles. So again, area of rectangles, these are just base times heights, but when we let n go to infinity, it doesn't matter if we use left or right hand sums, we're summing up infinitely many, infinitely thin rectangles. Of course, delta x is b minus a over n, and we have our mins and maxes by these notations. In that theorem, the same limit is attained for both mins and max values. So it follows from the squeeze theorem, remember the old squeeze theorem, that the choice of x in that ith subinterval does not affect the limit. This means we are free to choose any arbitrary x value in that ith subinterval, as shown in the definition of the area of a region of a plane. And here's that definition. So let f be some continuous non-negative function on the interval from a to b. The area of the region bounded by the graph of the function, the x-axis, and the vertical lines x equals a and x equals b is, that area is equal to the limit as we let n go to infinitely large or infinitely many rectangles, the summation from I equals 1 to n, f of c sub I, that's our height, times delta x the base, where x of subscript I minus 1 is less than or equal to c sub I is less than x sub I. That just means they are consecutive rectangles, and delta x, the base of any rectangle, is b minus a divided by that number n. Whew, that was a mouthful. And here we go with example 5, finding the area of a region by the limit definition. Now, I think this is an easy one. Yeah, and then we're going to do a little trickier one there in 6. So what we have now is x cubed, the cube function, from the x-axis and the vertical lines 0 to 1. Let me blow this up. So here's our x cubed opening up in the first quadrant. We want to go from 0 to 1. We want the exact area underneath that curve. When we get through, I think it's section 4.4, when we sort of get into the shortcut, we'll be able to do this problem in less than a minute. Very, very easy, but for now, we're going to go old school. So, oops, get out of there. So our area, using the formula we just checked out, is going to be the limit when we let n go to infinitely many rectangles. We are going to do the summation from I equals the first to the nth rectangle, f of c sub I, that's our function to dictate the height of the rectangle, times delta x the base. And because we could do either left or right hand sums, they're not telling us which to use. In this case, the right endpoint is going to be the easiest. So let's do right endpoint. We are starting at 0, so we could put 0 plus. We're just going to do b minus a over n times I. Ooh, and I guess we didn't find that yet. Our delta x is b minus a over n, and this problem cannot get much simpler. 1 minus 0 over n, or just 1 over n. So to figure out our right endpoint, we're just going to take 1 over n and multiply that by I. So our right endpoint is going to be I over n. We could do it with the left endpoint. That would be I minus 1 over n, but that's just going to give us more algebra work than we need. Oops, and why did I erase that? Oop, yeah, I guess I don't need that. Okay. So, area equals, we've got that. Let's put it, here it is in function notation. Now when we jump into the function, this time our function is x cubed. So we're going to have the limit as n gets infinitely large. The summation from the first rectangle to the last, something cubed, and that's going to be I over n, times delta x, and our delta x is 1 over n. I'm being very careful so you don't confuse my 1's with i's. There we go. All right, it's simplification time. Let's cube that one quantity and see what we can pull out in front of the summation. So we're going to have our limit as n goes to infinity at some point. I'm going to leave a little gap there for my summation from the first to the nth rectangle. And let's see, this is going to be I cubed when we cube this first term. So this is going to turn into an n cubed times this n. So it's going to be dragged out front as an n to the fourth, and it's in the denominator. Now our numerator, this is going to be a 1 here. I guess that 1 is just going to be what comes out, so that's a 1. So what is left after the summation? Well, the entire denominator, all the n's have been pulled out, so we're just left with an I to the third. And we got a formula for that. Okay. So let me copy this stuff. This is coming along for the ride. The limit as n goes to infinity, 1 over n to the fourth. Now I'm going to switch to black ink. I'm going to block off the summation and the I cubed. That's going to be replaced with our summation formula. And that is, remember, it's sort of like the summation of I. It's n times n plus 1 over 2, but we're going to square these. So that's an n squared, n plus 1 squared, 2 squared is 4. There we go. So let's do simplifying, canceling, and at some point we will let n go to infinity. If we let n go to infinity right now, we're going to have infinity over infinity, and that's not good. So, and to make our lives easier, right off the bat, we can cancel this n squared and knock this down to second power. So now what we have is our denominator. Denominator here is going to be 4 times n squared. That's 4n squared. And now we got left in the numerator n plus 1 quantity squared. Let's FOIL it out. N squared plus 2n plus 1. The limit as n gets infinitely large. Remember, n is our number of rectangles. We could plug in right now a 1 million for all the n's and get a very good estimate of that area under the curve. But why plug in a million and get an estimate when we can apply our limit rules and get the exact area? We are heading to infinity. We have a quotient. Which is more powerful? It's a tie. So we use a leading coefficient fraction. We have a 1 up here with the n squared. So that area is 1/4 units squared. And again, I said that we'll be able to do this computation in less than a minute when we learn the trick. That wasn't very hard at all, but it is going to get even easier. So again, we want the exact area under there. We've got the exact area, 1/4 square units. All right, moving right along. Example 6. Now it's also finding area by a limit definition. The big thing here is we're not starting at 0. So our left endpoint isn't just going to be our delta x times our I. We've got to account for this gap in between the y-axis and when we begin to accumulate our area under the curve. So we are now going to cut the interval 1, 2 into intervals. ERVALS. So our delta x is b minus a over n, or 2 minus 1 over n, or just 1 over n. That's not bad. But now let's figure out our right endpoint. Right endpoint. Again, we're not starting at 0. So this, if I don't want to flip back to it in the text, but it's a plus I times delta x. For most of our examples so far, a has been a 0, so we just leave it off. In this case, it's going to be 1 plus I times delta x. Here's our delta x. 1 over n times I is I over n. And I'm going to put it in parenthesis because it's kind of like a quantity. And let me make sure we can see that's an I. So there, our delta x is 1 over n. Our right endpoint, 1 plus I over n. All right, let me move this up here. And we're ready to get started. Area is equal to the limit as n heads to infinity. The summation from I equals the first rectangle to the last. And let me get this. Oops. I just need to shrink this up a little bit. There we go. That is going to be f of c sub I, again, just using our function notation, times delta x. So here is our, and I guess, well, we could have put in there, that 1 plus I over n is what's going to go in there. I don't feel like writing all that out again for another step. So let's just now jump it right into the function. And I'm going to squeeze this over. I'll barely be able to squeeze in my limit as n goes to infinity. Summation. Now here, let me bring it down again, our function is 4 minus x squared. So in here, we're going to have 4 minus something squared. That will be the height of our rectangles, and we're going to multiply that by the base, 1 over, n. What goes in here, though, is our 1 plus I. Come on, that's not going to stand. I over n. Okay, this is the height of a rectangle. 1 over n is the base of the rectangle. All right, so we've got our limit. We will let n go to infinity at some point. We have our summation, and we have 4 minus. Now I'm going to switch to blue ink and we're going to FOIL this out. Notice we are subtracting a squared quantity. So after we FOIL this out, we still want to subtract it as a quantity. So let's start FOILing. First times first is 1. Middle term is going to be this times 2. So that's going to be 2I over n. 2I over n. And then last times last will be I squared. Oops, not going to do it again. I squared over n squared. And close off the parenthesis. I can close off the brackets. And the 1 over n is still out here. Okay. So let's see here. I'm trying to minimize recopying as much as possible. We are going to distribute this negative and also distribute the summations. So let's kind of do that all in one step. The limit as n goes to infinity. So we're going to distribute the 1. So you're going to have a 4 minus 1 or 3. So we're going to have a summation of 3. And then we'll distribute that negative. So we're going to have minus the summation of 2I over n. 2I over n plus the summation of I squared over n squared. I squared over n squared. And what I should have done is put a big set of brackets so we could have the 1 over n out there. Or this 1 over n, we could just distribute it from the left. So each of these, let me switch to red ink, will have a 1 over n on the first summation. We'll have a 1 over n on the second summation. We will have a 1 over n on the third summation. Okay. Now we're going to look at each of those summations separately, pulling anything we can out to the left. Now I'm going to drop the limit notation for this one step. So our first one is 1 over n summation of 3 minus. Here we can pull this n out front, so that denominator is now an n squared, and we can also bring the 2 out, so the 2 is in the numerator, and that just leaves this as a summation of I. We have a formula for that. Plus our last summation, we have an n squared that's going to get pulled out. So now that's an n cubed in the denominator with just a 1 above it. And we have a summation of I squared. And we have a formula for that. Come on, piece of junk. I squared. Okay. And let me do this and move up. Upsy daisy. So I'm going to block this off in green ink. Our upper limit is n, so this becomes 3 times n over n. So 3 times n over n is our first term. We switch to green ink, back to green ink here. We have this summation of I, so we have a minus 2 over n squared, but that I is getting replaced with n times n plus 1 over 2. And then plus, we have 1 over n cubed, and then I squared. Let me go back to my green ink. Going to block that off, and that's going to be replaced with n times n plus 1 times 2n plus 1. Oops, back up there. There we go. Just make that a little smaller. So now we've got 1 over n cubed and our summation formula, n times n plus 1 times 2n plus 1, and that's all over 6. Okay, let's simplify each of those terms, and I might have enough room now to get my limit notation back in there. So the first term, 3n over n, easy, n's cross, we got a 3. Minus. On the next one, we can cancel the 2's on the diagonal, and we can cancel this n with one of these down here. So that's nice. We're going to have an n plus 1 over n. N plus 1 over n. And that takes care of this middle term. And now plus our last one here, we have an n here, we'll cancel. Now this is down to squared. So my denominator for this one is a 6n squared. And we FOIL out the numerator. Same two binomials again. So that's a 2n squared plus a 3n plus 1. So let's apply the limit. We're going to let n go to infinity. So the first term, there is no n there, so that's just going to be a 3 minus. Here, what's more powerful, numerator or denominator? It's a tie. So we do our leading coefficients. 1 over 1 is 1. Plus, in our last one, what's more powerful? Yet again, it's a tie. So we get 2 over 6. That reduces down to 1/3. And I just caught a mistake of mine. When we were distributing the negative across the three terms, this plus right here, that should be a minus. Again, I'd hate to have to stop this video, go back and re-record it because I forgot that minus. I've erased enough stuff. I've lost where I did that. But this plus should be a minus. So that's going to make this plus into a minus, and that makes this into a minus. Okay, so now we've got 3 minus 1 minus 1/3. That's going to be 2 minus 1/3. That is 1 2/3 or 5/3 units squared. Oh, there we go with only one minor mistake on my part. I forgot to distribute that negative, but it is not the end of the world. We got the exact area under that curve. We are almost done. Actually, we've got 2 more examples. Wow, this might be kind of a long video. Example number 7. What if our region is not bounded by the x-axis, but by the y-axis? So we can pull that off, no problem. We just got to tilt our heads 90 degrees. No, I'm just kidding. So here now, we're going from the y-axis 0 to 1. We're bounded by the curve, and our now rectangles are going to be perpendicular to the y-axis. So we're not going to be finding a delta x. Remember, delta x was the base of our rectangles. This time, it's going to be a delta y, but the idea is the same. B minus a over n, or 1 over n, is the base of our rectangles. And now our our area is still going to be a limit when we let n go to infinitely large, and our function f of c sub I will still dictate the height of those rectangles, and delta y will be the base. Now the big thing here is our function must be in terms of y, and they gave it to us in terms of y. So we are sort of good to go here. So our area is going to be the limit as we let n go to infinity. I guess we got to find our right endpoints, or I guess in this case we could call them our upper endpoints. That is just going to be this delta y times I. So once again, it's going to be I over n. So delta y is 1 over n. Our endpoint formula is I over n. And we're putting that into the squaring function. So we're going to do a summation from the first to the nth rectangle of I over n, quantity squared, because we're dealing with the squared function, times delta y. Delta y is 1 over n. Okay, let's see what we can simplify and pull out in front of the summation notation. We're still going to have our limit. We want n to go to infinity when we can. We have our summation from the first to the last rectangle. Now, of course, we are going to square both of these, so that's going to be an I squared over an n squared, and we can drag out our denominators as an n to the third. Our numerator is just going to be a 1, and that's going to just leave us here with an I squared. And we have a formula for that. So our limit, limit, as n is heading off to infinity, we have our 1 over n cubed. I squared's formula is n times n plus 1 times 2n plus 1 all over 6. Look for that cancellation on the diagonal of one of your n's. Makes our algebra a little easier. So this n is gone, and this is now down to squared. So our denominator is going to be a 6n squared, and we FOIL out the numerator. 2n squared plus 3n plus 1. We are ready to send our limit off to infinity. Once again, we have a tie. Cancel the n squareds. Our limit is 1/3. 1/3 squared units to find that area between the curve and the y-axis. Okay, now this last one, this is kind of new to the newer edition of the book. It says here in examples 5, 6, and 7, c sub I is chosen to be a value that is convenient for calculating the limit, because each limit gives an exact area for any c sub I. There's no need to find values that give good approximations when n is small. For an approximation, however, we should try to find the value of c sub I that gives a good approximation of the area for any subregion. In general, a good value to choose is the midpoint. Apply the midpoint rule. Because think about this, in all of these we've done so far, let me back up, back. I want to find a good one to zoom in on, so to speak here. No. Aha. You know, on these, we did left and right hand. Either we were completely below or we extended a good amount in between. Let me blow this up some more. What if, let me just pick this rectangle here. This is rectangle number 4. What if we went up until we hit at the midpoint and then went across? Notice here now, we've got a little, I'll use red here for area that we should have counted but didn't, and I'll use blue for area that we did count but shouldn't have. So if we use a midpoint, we get a little positive and a little negative area on any rectangle. And they're kind of going to cancel each other out a little bit. So instead of left-hand sums or right-hand sums, we could use midpoints. Now, a word of warning to my people taking the AP test. These do pop up on the free response AP test from time to time. These ones, though, they usually keep them to a limited number of rectangles. In this case, n is 4. They usually stay between 4 or 5 or 6 rectangles. And these are actually, I like these better than doing them with all the formulas and finding exact values. So let's start this. Let's read through it. Use the midpoint rule with n of 4 rectangles. Approximate the area of the region bounded by the graph of the sine wave from 0 to pi. Remember, sine is going to go from 0 to pi, and then underneath from pi to pi over 2, back when we were graphing those in pre-calc. So let's just start this off like we did all the others. Delta x, what is going to be the base of any rectangle? So we're going to go from b minus a over n. So that is pi minus 0 over n, or we're doing 4 for our rectangle, so I should have put that n as a 4. So that's just pi over 4. Delta x is pi over 4. That is the base of any of our 4 rectangles. What we need to do now is find the midpoints of each of those bases. Of each of those rectangles. Now we could just look at the picture. Here's one way to do it. And say, okay, I need that first midpoint. What's right in between 0 and pi over 4? Well, remember what I taught you last year, just double that denominator. So our first midpoint would be pi over 8. And then we can count by eighths. 1 pi over 8. That's 2 pi over 8. So our next midpoint would be 3 pi over 8. Then this one is 4 pi over 8. Here would be 5 pi over 8. 6 pi over 8 is an endpoint. And then here we would have 7 pi over 8. So there we can get them graphically by looking at the picture, or you could find each midpoint. Midpoint is going to be your left endpoint 0 plus your right endpoint pi over 4, cut it in half. So that would be for this one. Our next one would be pi over 4 plus pi over 2, cut it in half. And then we would do pi over 2 plus 3 pi over 4, cut it in half. Plus 3 pi over 4 plus pi, cut it in half. So there are two ways to go about finding those midpoints, but I'm just going to list them here. Midpoints are 1 pi over 8, 3 pi over 8, 5 pi over 8, and 7 pi over 8. So we have 4 rectangles, we have 4 midpoints. Let's go back to our notation. Area equals the summation from I equals 1 to the nth. And let's just jump right into the function. This is going to be the sine of c sub I, whatever that midpoint is, times pi over 4. Remember, in the big scheme of things, this will give us the height of any rectangle. Pi over 4 is the base of any rectangle. So here's how I like to approach these now. We've got 4 rectangles. Area equals, now I'm going to keep this abstract as possible. We have base times height 1 plus base times height 2, base times height 3, plus base times height 4. These are our 4 rectangles, base times height for each of the 4. Notice that one of those is the same for all of them. So we can factor out the base. When we factor the base out, we're going to have height 1 plus height 2 plus height 3 plus height 4. Well, our base is pi over 4, and then our heights come from the sine of our midpoints. So our first height is going to be the sine of pi over 8. Plus our next rectangle's height is going to be the sine of 3 pi over 8. Plus our third height is going to be the sine of 5 pi over 8. Plus our last rectangle will be the height will be sine of 7 pi over 8. From here, you just punch it in on the calculator. Beep, 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 add them up, multiply by pi over 4, you get approximately 2.052 square units. Again, if they're limiting your numbers 4 to 6, this is an easy way to go. Just think about it as the sum of some number of rectangles, factor the base out, then you have the base times the sum of the heights. And there's our midpoint estimation of that area. Is that the last one? Hallelujah. The second video is over. Next time I see you in class, we'll do some worksheets and or odd problems. I'll see you then.